So now that we have a clear understanding of how elementary row operations affect determinants, the next question that you might ask is how are determinants affected by the matrix operations, such as addition, subtraction, scalar multiplication, or matrix multiplication? And that's going to be what we take a look at next. So I want to start by considering a few expressions. So let's say we have a couple of matrices A and B, and let's say that they're square of the same size, which really is what this says here, right? For n by n matrices A and B, that's just saying that they're square and are of the same size. And let's say we also have a scalar, which we'll call k. Okay, so let's consider the three expressions that I write down here. The first one is the determinant of the matrix that you get if you multiply A by the scalar k. Right, and that's a sensible mathematical expression because if A is an n by n matrix, then Ka is an n by n matrix. So we really do have a square matrix in here, so taking its determinant is completely fine. Another thing you might consider is the determinant of the product of A and B. Right, and again, that makes sense because if A is n by n and B is n by n, well then the product of A and B is also going to be n by n. So again, we have the determinant of a square matrix, so this is completely sensible as well. And lastly, I'm going to write down the determinant of A plus B. Right, and again, that makes sense because A and B are both n by n, so is their sum. So you have the determinant of a square matrix here as well. So the question that we're going to ask more formally is which of these expressions have relationships between the determinant of just the original matrices A and B, right? That's the question that's asked here. And well, the answer is these two. These two can be expressed in terms of the determinants of the original matrices A and B. It turns out that this one can't, except under very specific circumstances, which I'm not going to get into right now. So in general, this expression, determinant of A plus B, you would just have to add the matrices together and take the determinant directly. You would not be able to take the determinant of the two matrices A and B separately and then say add them, for example, and expect to get this value, because it just won't happen in general. But it turns out there's good news for these two expressions. So we're going to start by taking a look at k times a. So anyways, yeah, the answer is the first two. These two can be expressed in terms of determinant of a and the determinant of b, but this one can't. And same for subtraction. It actually turns out to be the same for subtraction. Okay, so a reminder here. This is how we're going to answer the question of how can you express this first expression, determinant of k times a, in terms of the determinant of a. Well, the first thing I want to remind you of is that remember that if you can take a matrix A, a square matrix A, and carry it to the matrix B by performing this single row operation, by multiplying one of the rows by a constant k, well then it turns out you change the determinant by a factor of k. So what you can say is that the determinant of B is equal to k times the determinant of A. Right, and I'm going to just put this one in green because it's not new. Right, we've already talked about this in the previous section, but I do want it to be at the forefront of your brain because we're going to use it now in just a moment, in the next sentence actually. So let's read this carefully. Since any matrix A may be carried to k times A, so here you got another matrix k times A. Think about it this way. How can you turn a matrix A into the scalar product of k times A by just using row operations? Well, what happens if you multiply a matrix by a scalar? What does that do? Well, you have the effect. It has the effect of multiplying every entry of the matrix A by the scalar k. So one way to do it would just be to take each of the rows of A and multiply them by the scalar k. And really, how many row operations are you doing? Well, you're doing one operation for every row of the matrix A. So if we stay with the original assumption that A was n by n, so A has n rows and n columns, well, then the determinant of k times A, you can write it down in the following way. Because if you can turn A into k times A by multiplying each of the rows one at a time by the scalar k. And every time you do that, every time you multiply one of those rows by k, you're going to change the determinant by a factor of k. So you're not just going to do it once, but you're going to do it n times, once for every row of the matrix A. So if I were to write k times the determinant of A, that would be incorrect, because that would fail to take into account the fact that by multiplying the matrix A by the scalar k, you're actually multiplying every single row by k, not just one row by k. So what the fix is just put an exponent of n here. You're no longer changing the determinant by a factor of k, you're changing it by a factor of k to the power of n. One factor of k for every single row of the matrix A. And this one is a new formula, so I'm going to circle that one in red. So let's take a look at an example of what this looks like. Well, we've got a 3 by 3 matrix here, and if you look closely, you'll notice that every single one of the entries in this matrix is a multiple of 3. So for that reason, I can write the following. I can say, okay, A is equal to this matrix. Well, it's also equal to 3 times the following matrix. I'm just going to write this as 3 times the matrix 1, 3, 4, negative 2, 6, 7, and then 0, negative 1, and 1. So that's the first thing we're going to observe. And since that's the case, well, then I can do the following. I can write the determinant of the matrix A. Well, if I just take a moment to change notation, I'll have, this is the determinant of 3, 9, 12, negative 6, 18, 21, and 0, negative 3, 3. Right, I'm just changing notation and writing it out as a 3 by 3 determinant. Well, what I'm going to do is I'm going to pull out the 3. This is how you can think of this rule. Just pull out the 3 from the determinant, and I'm going to get, you're essentially pulling out a 3 from every single one of those entries, and I'll have 1, 3, 4, negative 2, 6, 7, 0, negative 1, and 1. Now that is currently not quite correct, right? Because what I've done is I've made the mistake of forgetting to take into account that I didn't just pull a 3 out of a single row, I pull it out of all 3 rows, essentially, right? If I factor it out of the entire matrix. So based on this rule, with k equal to 3, and what's n? Well, n is the number of rows and columns of the matrix A in this formula. So this matrix A in this example has 3 rows and 3 columns. So I need to put this n here, right? This is really what you're doing. This determinant is this determinant. This determinant here is this determinant here. So what we're going to do here is just put a 3 there. It's really just that it's not just 3 times the determinant of A, it's 3 to the power of 3 determinant of A. That's where that 3 is coming from, this n. So with that in mind, well, no problem. 3 to the power of 3 is 27. So you have 27 times this determinant that still needs to be worked out. So we can do that on the next line. Why don't we work this one out directly? So 1, 3, 4, negative 2, 6, 7, and 0, negative 1, 1. Getting a little bit. We've written this out a few times now. That'll be the last time. Let's do cofactor expansion. How about the first column, since it's got a 0? Right? That if we're going to do cofactor expansion, the first column is probably a good choice to use. So we'll get 1 times the corresponding minor, so the determinant is 6, 7, negative 1, and 2. Or 6, 7, negative 1, and positive 1. I don't know if I said that wrong a moment ago, but I'll just say it again just to be sure. Okay, so that's the first term is we need 1 times this 2 by 2 determinant. Then we're going to have minus negative 2, because of that negative 2 that's right there, times the determinant of the 2 by 2 matrix consisting of the 3 and the 4, and the negative 1 and the 1. And then the last one, the entries is 0, so we could skip that one. So this is our cofactor expansion, and well, this one here, this is going to be equal to 6 times 1 minus 7 times negative 1, which is really just 6 plus 7, so that's going to be 13. And this one here, what do we got? We've got 3 times 1 minus 4 times negative 1. So that's minus negative 4, or in other words, it's plus 4, which just gives us 7. So what we really get here, if we plug those in, is what we get 1 times 13 minus negative 2, so this is just really plus 2 times 7. So that's going to be 13 plus 14, which ends up being 27. All right, so this is actually that 27 is still out there. This 3 by 3 determinant turns into a 27. So we actually get 27 times 27. And if you punch that into your calculator, what you're going to end up getting is 729. So that's just an example of using this property. Do you have to do this? Could you just compute the 3 by 3 determinant directly? Absolutely. You could just do cofactor expansion along any row or column for the matrix A, or maybe you want to do some row operations. Right? That's another option that you have available to you. It's not that this is the only way to calculate the determinant, but it's just an example of how you could use this property, and it just shows how it works.